In this session, we are going to cover an important concept in functional programming. Higher order functions let you pass functions as arguments and return them as results. One thing particular about functional languages is that they treat functions as first-class values. This means that, like any other value, a function can be passed as a parameter to another function or returned as a result. We'll see in this session that this provides a flexible way to compose programs. Functions that take other functions as parameters or that return functions as results are called higher order functions. So that's the opposite of first order functions. A first order function would be then a function that acts on data types, simple data types such as ints or longs or lists, but not other functions, whereas a higher order function acts on other functions. Let's see an example. Let's suppose we want to take the sum of all the integers between a and b. So we could write something like this. Sum ints, it takes the bounds as parameters, the a and the b. And we ask, well, if a is greater than b, then there's nothing to sum, and we would return 0 as the logical value for that. And otherwise, we would return a plus a recursive call of sum ints of a plus 1 and b. Good. Now that we've done that, let's vary the problem a little bit and consider taking the sum of the cubes of all integers between a and b. So here's the cube function. Take an x, return x times x times x. Sum cubes then would be the same as sum ints, but where we used an a before, now we return cube of a. And otherwise, it's the same thing as sum ints, recursive call to sum cubes in this case. Next, let's take the sum of all factorials of the integers between a and b. Well, you see the principle by now. The program again is exactly like sum ints and sum cubes, except that where previously we computed the cube, we compute the factorial. Of course, these are all special cases of the mathematical sum of values of f of n, where f is a given function and n is taken from the interval between a and b. The question is, well, if mathematics has a special notation for that, shouldn't programming have one as well? Can we factor out the common pattern into a single method? So here's how that's done. Let's define a function sum, which takes a parameter f of type int to int, and the two bounds a and b, both ints. And let's generalize the previous three definitions as follows. We write if a greater than b, then 0. Otherwise, take f of a plus sum of f and a plus 1 b. So the new thing here is that f is a parameter of the sum function. It's not a given function, it's a parameter. Once we have that, we can then write our function sum ints, sum cubes, sum factorial as follows. Sum ints would be simply sum of id of ab, where the id function simply returns its parameter unchanged. Sum cubes would be sum of cube and ab, where the cube function is as what we've seen before. And finally, sum factorial is sum of fact and ab, where the fact function is again the factorial function. So what we've done effectively is reuse the pattern that defines the sum function, so that we had to write that only once, and we could reuse it in the three definitions of the particular sums. One thing that's new here is a function type. A function type is written a arrow b, where a and b are types, and it's the type of a function that takes an argument of type a and returns a result of type b. So for example, int arrow int is a type of functions that map integers to integers. Looking at the previous example again, we have successfully shortened the definition of sum ints, sum cubes, sum factorials, but there's an annoying detail. We had to name all the little auxiliary functions that we do here. So we've gained some program code here, but we've spent more in the definition of all these auxiliary functions. So we've seen that passing functions as parameters can lead to the creation of many small functions, and sometimes that's tedious. Compare the situation to other types, such as strings. We could write something like def str equals abc and then println str, but we don't have to. We can just as well write println abc directly, and that's because strings exist as literals. Since functions are important in our language, it makes sense to think of introducing literals for functions as well. And that's what we do next. These literals are called anonymous functions because they do not have a name. So here's how we write anonymous functions. As an example, let's consider the function that raises its argument to a cube. That would be written as you see here. So it takes a parameter x of type int, and then there comes an arrow, and then comes the value of the function, in this case x times x times x. So x colon int is the parameter of the function, and on the right hand side of the arrow is the body. In fact, the type of the parameter can be omitted if the compiler can infer it from the context. And if you have several parameters, you can write them in a list separated by commas. So for instance, that function here, what would that be? Well, yes, the summation function, so it would take two integers, x and y, and give you the sum of x and y. You could ask, are anonymous functions essential for Scala, just as, let's say, conditionals or value definitions are essential? Or can they be defined in some other way? It actually turns out that every anonymous function can be expressed in some other way using a def. So let's say you have an anonymous function with n parameters, x1 to xn, and a body e. You can always write this as the function def f, then come the parameters, then comes the body, and then you follow that by a reference to this function that you have just defined. Sometimes you might have to write the expression in a block so that the name doesn't get confused with something else. Because we can always rewrite anonymous functions, we can therefore say that they are syntactic sugar. They make writing functions sometimes easier, but they're not essential in the sense that they do not add anything to the fundamental expressive power of the language. So to come back to the sum ints and sum cubes example, using anonymous functions we can write these now in a shorter way. Sum ints would be just the function sum, where the function we pass is the identity function written x arrow x, and the bounds are the parameters, and sum cubes would have as the function parameter x arrow x times x times x. And if we do that, then we do not need anymore the auxiliary definitions of identity or cube. Let's do an exercise. The sum function uses linear recursion. Can you write a tail recursive function instead? Note that unlike factorial, sum really could profit from this tail recursion optimization. Because of the interval between a and b is large, you might get a lot of different recursive steps, so you might risk a stack overflow. So let's rectify that and design a tail recursive function instead. I've already given you a template for this function. It uses a nested function loop, and all you have to do is replace the triple question marks here and here. So let's see how we would go about that. The first one here is in the loop function we have a test that says, well, if something's true, then probably that would be the termination. So when do we terminate? Well, we terminate if the lower bound a is greater than the upper bound b. And what do we return in that case? Well, since we have used the accumulator trick, we would return the accumulator. Once we have that, we can look at the initial call. So as the first parameter, we would pass the initial lower bound a, and as the initial accumulator would have to be what? Well, we know accumulator is the result that we return when the interval is initially empty, so that would have to be 0. And finally, in the recursive call, we would assume that the initial bound gets incremented by 1, and the new accumulator is f applied to a plus the previous accumulator. We can test this function. Let's apply this function to lower bound 3, upper bound 5. and we would get 50 as expected. You have seen higher order functions as essential building blocks of functional programs. In the next session we are going to play a little bit more with higher order functions and introduce new ways to express them.